Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience. Hi everyone, today we have with us Tim Dreier, who is a postdoctoral research associate at the Center of Integrated Nanotechnologies at Sandia National Laboratory based in New Mexico, USA. Hi Tim, how are you?
Hi, I'm good. How are you doing?
Wonderful, wonderful. Very, very happy and excited to speak with you. Let's start with you telling us the story of how did you end up in your current research field?
Well, it's long. I'll try to keep it short.
Okay.
Many years ago, I worked as a bank analyst and I didn't like it. So I went back to school and got a degree in chemistry, and then I went to graduate school also in chemistry.
Mm-hmm.
I started out working on organometallic chemistry, and then at the halfway point of my PhD, moved into a different lab to work on gold nanocluster chemistry. So nanoclusters are like nanoparticles, but we sometimes call them ultra small nanoparticles, where you know what their chemical formula is. So they're very large molecules. Like I mostly worked on gold 25, so 25 gold atoms with 18 ligands kind of on the outside. And so my doctoral work ended up taking this turn where I applied techniques from organic chemistry to understand reactions at the nanoscale, like how particles form from synthesis. And so when I defended and graduated, I took a job related as a postdoc at Los Alamos to make some nanoparticle polymer composite materials. And try to understand how those reactions worked and how we could tune them to make materials with the kinds of properties we wanted for light matter interactions and these sorts of things. Well, we'll just say, so when my appointment ended there, I had been looking for a job. I took one shot at the faculty market, got a number of interviews and no offers. And so I took this position after, interviewing for a bunch of other ones, because it was doing something more related to where I wanted to be long-term, more fundamental, related to particle synthesis and understanding reactions of nanoparticles. And the project seemed really interesting. It was something I hadn't really worked on before. So I ended up working on magnetic nanoparticles, which is not something I had touched prior to the middle of October when I started. And that's great because I've gotten to learn, I'm getting to learn some really cool new stuff and new instruments and new techniques that'll be good for my independent career. But it was a little bit of a circuitous route, but because of my interests in fundamental chemistry, especially fundamental chemistry as it relates to making nanoparticles, that's kind of where I ended up.
Okay, that's quite an interesting journey you've had from being a bank analyst to being a postdoc now at a research lab. That's really interesting. So I'm sure you have done quite an interesting set of you have a quite a wide knowledge of the field. So could you explain to us where does your current research fall in this big picture of this domain of materials and nanoscience?
So the whole of my research up to this point, from graduate school to what I'm doing now, falls into really the domain of trying to understand how nanoparticles get made in the reactions that make them.
Right.
And specifically right now, what I'm working on are magnetic nanoparticles, very, very tiny magnets, because we can use those for all kinds of things. The big one is a part of electronics and transformers called an inductor, which I don't understand very well, but I know they're part of transformers, and one big problem is they're only so efficient. And even if they're very, very efficient, when you get up to like a grid scale, right, you have a lot of them, those small inefficiencies add up. So if you use very, very small magnets, nanomagnets, in those kinds of applications, you can improve the efficiency, and that leads to massive energy savings.
Right.
You can also think about nanoparticles as a way to store memory magnetically. So that's kind of where things fit in. It's really understanding how nanoparticles get formed in reactions so that we can then play with those reactions to get them to make things we want them to make. Particles of a particular size, particles with particular magnetic properties or compositions or these sorts of things.
Okay. All right. That sounds super interesting. So it sounds to me that you have done quite an interesting bunch of experiments. So could you, if you had to pick one, could you pick one experiment as your favorite, or the one that you're most proud of, and explain it to us in simple words in the section we call In Other Words?
Sure. So the thing I am most proud of is really, really obscure. It's a really obscure topic. But a number of people had pointed to gold-25, so it's with 18 thiolate ligands, so it's 25 gold atoms, 18 organothiols, sulfur and some stuff hanging off it, as catalysts for different kinds of reactions. They kind of missed some of the control experiments in these reports.
Right.
And so I essentially sat down in the lab and did one very, very simple experiment where I did the reaction, and I analyzed the outcome to see if the nanoclusters were still there. And they weren't. And we were able to expand that into a really very thorough set of reactions and work that pretty conclusively demonstrated that under these reaction conditions, the nanocluster came apart before any of the chemistry happened, and that it was actually individual gold atoms doing all of the chemistry that had been assigned to these larger gold molecules. So that's probably the thing I'm most proud of, just even though it's not probably the most important, just because it was real good demonstration of how some good luck and a little bit of good thinking can really lead to interesting results.
Right.
People forget a lot, I think, that there's a surprising amount of luck involved in laboratory science.
Yes. Yes. No, that sounds like a very, very interesting an important piece of a puzzle. I mean, that is usually might not be the most glamorous, might not be the most attractive part, but every piece in a puzzle is very important.
Yeah, and it's the kind of chemistry I really like, where it's like, here's this weird observation. How does that work?
Right.
What's fundamentally going on at the atomistic or molecular level that's causing this behavior? Because those are the kinds of problems that really I'm very excitable about.
Well, you are a true researcher. You are a true scientist. I can see that. And I hope your research experience so far has been wonderful and will continue to be wonderful in the future as well. However, if you had 3 wishes to improve your research experience, what would you ask for? And disclaimer, not promising anything here.
Well, you're not a research experience genie. You can't.
Sorry.
You can't magically make. At the moment, overall, any career has ups and downs.
Right.
Overall, at the moment, I'm pretty happy with where I'm at. I think I'm in a good spot.
Okay.
What I think could really improve things, generally speaking, would be, number one, to make sure people who mentor, have graduate students, have postdocs, actually have the skills for it. Management training, conflict resolution training, communications training, because we have this career in science where you spend Let's see. I started graduate school in 2011. I worked as an undergraduate for a couple of years. I spent more or less the last 10 years getting really good at doing experiments.
Right.
And then my next job will be asking for money and managing people.
Right.
And I haven't been trained for that. So that's a whole other thing to learn.
Right.
Number two, I think, is that the treatment and pay for graduate students just straight up needs to be better.
Mm-hmm.
I think that, fortunately, I'm no longer affected by this particular one, but you don't get paid much when you're in graduate school, at least in the U.S.
Right.
Other countries I know are different. Sometimes you're expected to work ridiculous hours. Your mentor has a ton of power over your future career.
Right.
And your current paycheck.
Right.
I think it's what's the saying? I think I heard this from Chem Jobber the first time. Is your advisor holds your paycheck in one hand and your rec letter in the other.
Oh, yeah.
So, we're in this situation where, a lot of folks in graduate school are really struggling both with, just making the bills and with, life.
Mm-hmm.
And so I think decent pay for the labor that they actually do and benefits commiserate with their level of professionalism.
Right.
I think that would be number two.
Okay.
Third wish, if I could just get rid of, hero worship, generally speaking. I could just wave that out the door, because I think it's when you put somebody on a pedestal and stop evaluating their work in its context or on its own merits, I think it leads to bad decision making, especially when you're trying to solve a problem or get closer to something we might call the truth.
Right. Right. Okay. All three fair wishes. I wish I could grant them, but I would like to believe that we are working towards at least solving the first and the second one. The third one might take a while because you have to change the mindsets and not just open your pockets. So it might take a while, but I'm glad that our future researchers are already mindful of this. And you are a researcher, and in the future, you are the future of science, and you are the future of research. It's good that not putting you on a pedestal.
Well, I would just say that there are more talented, harder working, smarter people who I hope are the future. I'm happy to participate and do my part.
That's very modest of you. That's very modest of you. All right. I wish I could grant them. However, I can't at this point. But as soon as I get my magic powers, I give you a call, and
Great.
we make everything happen. Okay, wonderful. Let's move on to a little bit of the future now. Speaking of future, what are you most looking forward to in the next 3 months?
So, as I sort of mentioned, I'm new to electron microscopy. I hadn't done very much as a graduate student because the nanomaterials I was working with were too small to actually see well on an electron microscope.
Okay. What did you use to see them then?
So you can solve them crystallographically. And gold 25 in particular has a very characteristic UV visible signature, which you can observe. It's too small to have a plasmon. We can edit that out. But but in any case, we used other techniques like crystallography or UV visible spectroscopy to identify what we had made. Because gold 25 is about 0.9 nanometers.
Right.
So it's a
small.
It's only 25 atoms.
Yeah.
So it's very, very difficult to observe that on an electron microscope without beam damage.
Right. Okay. All right. That's interesting. Okay. Cool.
But in any case, I didn't do a lot of electron microscopy as a graduate student. I maybe used the instrument a couple of times, and so now I'm getting to do some electron microscopy and learn some new techniques, and I like that. That's always fun. So it's another thing I get to know about. And I'm working with one of our really good microscopists here, John Watt, on doing some observations of reactions occurring at an iron nanoparticle surface, really an iron oxide nanoparticle surface.
Right.
You can make a bunch of different kinds of iron oxide, and we're looking at one turning into another in real time. We've
Wow,
got
that sounds so cool.
yeah, it's super exciting. I'm really excited about it.
Could you send me the video when you're done, when you're ready with this experiment?
Yeah, I'll make sure that. I mean, we're gonna publish it eventually, but yeah, when we're working out the kinks with the actual procedure, because it's really hard to get something from a glove box to a microscope without ever exposing it to any air.
Yeah.
But yeah, I'm really excited about that. We have this fancy loaner camera on the instrument right now from Gatan. They like lent it to us, and it has to go back pretty soon. So we're trying to get all the stuff done as fast as we can. And
Right.
So I'm really excited about that. We're trying to observe a couple of different crystallographic rearrangements and chemistry changes on the surface of iron nanoparticles.
Right.
Because it hadn't been done before, and it'd be really cool.
Yeah. It sounds very cool. Okay, wonderful. That's cool. I look forward to the video. Before we end, could you walk us through the challenges or the big questions that the field of nano and material science is facing or trying to solve right now? The researchers like you are trying to solve the big questions. What are they?
I mean, that of itself is a big question, right? Because
Yeah.
you ask 5 scientists, you get 10 answers. There are so many really interesting, exciting problems going forward. Everything from energy storage, like batteries, energy conversion for solar cells, things like I'm working on with magnetic materials for energy conversion and storage materials and memristors and all this kind of stuff. So there's just so many really exciting problems.
Right.
The one that I think kind of ties everything together and is really fundamental to a lot of those different challenges is understanding how nanoparticle formation reactions really work on an atom by atom basis, on a molecule by molecule basis. Right. Because if we think about the 20th century, right, from a chemistry perspective, and I'm a synthetic chemist by training, so that's the way I think about problems and the way that I consider science. Organic chemistry got to really be in charge of a lot of chemistry for the 20th century, like starting, in the 50s with Brown and Bob Woodward and all this. And the reason for that, I think, is that we understand and can understand how organic chemistry reactions work on a really fundamental level. Right. Like you can say, well, okay, so this bond breaks and then these electrons make this new bond and here's what's going on. At the nanoscale, we don't understand that very well. We have some models, a couple of pretty famous ones, the Lemur model, which is, you can look that up. The Finke-Watsky model, you can, if you're interested, you can Google these things. Because it's I could try and explain them, but it would take forever.
You can explain them when you're taking over the account.
Sure. But the issue is that they don't really tell us how the bonds get broken and formed in these nanoparticle forming reactions. Right. They tell us about rates. They tell us how fast stuff happens. They have some insight into intermediates, like what is formed along the way.
Right.
But we don't really understand how things work on a, first this bond gets made, then this other one, then this other one. And to a certain extent, that's understandable because making, say, a 5 nanometer particle, right? That's a lot of steps from here's one gold atom or here's one iron atom to here's a particle that's 5 nanometers in diameter and has 4,000 roughly atoms in it if it's gold. So if we can get to a place where we understand all of those intermediate steps and understand how reactions fundamentally work at the atomistic level in nanoscience, I think that opens up a whole new world of materials design and synthesis, because you can say, oh, I want to make this thing. Well, okay, how do I get there? Well, the reaction works in such a way that if I push this button and this button and this button, I can get what I want out. And we have some of that now, but it's empirical. It's not based on a mechanistic understanding. It's, well, I know that if I put these three things in and I vary the conditions this way, I get a 10 nanometer particle instead of a 5 nanometer particle. Do I know why? Not really. Do I care? Maybe. And I think that mechanism issue, that fundamental, this is what's happening in the flask, I think that's a really exciting and important problem that has implications for tons of syntheses. And I think it'll be, I don't think there's a general solution. I think that every kind of synthesis probably has its own mechanistic quirks, you know? Yeah. Right. Just like, you know, I've got a book on my shelf from graduate school that's got, you know, a couple of hundred named organic chemistry reactions in it. And I'm sure the same thing is kind of true in nanoparticle formation, but I bet we can get there with the right experiments. So that's what I'm really excited about, is that kind of problem.
To understand the small to solve the bigger picture, or to understand the bigger picture.
Right. So we have an atom of gold. We have a 5 nanometer particle of gold. We've got some stuff in the middle. How exactly do we go from atom to particle? What are the exact steps? Where do the electrons go? You know, that's really what I think is a fundamentally important and exciting problem for the field. Other people probably disagree, and that's fine. They're probably also right.
Yeah,
I mean, right in the sense that there are so many excellent problems to be working on, and your own knowledge and experience and interests are only so big.
Yeah. So. Everyone's got a different perspective, and I think I agree with your perspective as well when you say that, well, to understand exactly how things are moving, and that really this podcast has shown me, or proved to me in the little time that we have spent together over the screens, is you're a true scientist. At the core of your way that you think, you are a true scientist. So it's great to have you on Real Scientist Nano.
Well, thank you. I appreciate it. I'd like to emphasize that, you know, all the obscure stuff and facts and whatever and way of thinking that I have, I didn't used to. You know, I'm just some guy who couldn't find the exit on a classroom and ended up staying. So, you know, I hope to kind of make what I'm working on accessible to folks. You know, and for them to be able to see that scientists are just, you know, we're just people who have a particular kind of expertise and job.
Yeah.
You know.
Yeah. Yeah, that's also our goal, to bring the humans behind the materials and nanoscientists forward, and also the science from the scientists themselves. So this is great. It has been lovely speaking with you, Tim. Thank you very much for speaking with us, and we are looking forward to having you on Real Scientist Nano.
Well, thank you very much for having me, and I'm looking forward to curating the account.
Wonderful. Thank you for listening. To know more about us, please visit our website, realscientistsnano.org, and follow us on Twitter at realsci_nano.